In this slide, we will discuss an important part of the CPU scheduling mechanism in operating systems, the dispatcher. The dispatcher is a module that works silently in the background, but it plays a crucial role in making sure that processes run smoothly and can switch between each other. The dispatcher's main job is to give the CPU to the process that the CPU scheduler has chosen. It is like a traffic officer who makes sure that processes can switch between each other in an orderly way and that they don't have to wait too long. Here are the steps that the dispatcher takes when it switches control between processes. First step, switching context. The dispatcher saves the current state of the process in its process control block. This includes the processor's program counter, registers, and other important data. This is like bookmarking a page in a book. Second step, switching to user mode. By default, many operations are executed in kernel mode, which gives the operating system full control over the system's resources. However, before a process can start running, the dispatcher must switch the CPU to user mode. This makes sure that processors cannot accidentally access important system areas. Third step, jumping to the correct location. Finally, the dispatcher makes sure that the process picks up where it left off. It does this by moving the CPU's program counter to the correct location in the process. This is like going back to the bookmark page in a book and resuming reading. Dispatch latency is the amount of time it takes for the dispatcher to stop one process and start another. It is important to minimize dispatch latency because high latency can cause noticeable delays for users and make the CPU less efficient. The diagram in the slide shows an example of dispatch latency. Process P0 is running, and its state is saved in its PCB when it is preempted. Before the next process, P1 can start running, its state is loaded from its PCB. The time between when P0 is stopped and when P1 is started is the dispatch latency. The dispatcher, though behind the scenes, ensures the seamless execution and transition of processes. In our previous slide, we discussed dispatch latency. In this slide, we will take a closer look at how dispatch latency affects real-time systems and process response times. An event is something that happens that needs the system's attention right away. Events are often external, meaning that they happen outside of the system's control. In real-time systems, it is very important to respond to events in a timely manner in order for the system to work properly. When an event happens, it usually causes an interrupt. This forces the operating system to stop what it is doing and deal with the event. The amount of time it takes from when the event happens until the system starts processing the interrupt is called the interrupt processing time. Once the system has acknowledged the interrupt, it needs to find the right process or thread to handle the event. It also needs to get that process or thread ready to run. It is important to be able to find and get the right process ready quickly so that the system can respond to the event quickly. As we discussed before, dispatch latency is the amount of time it takes to stop the current process and start running the process that was chosen to handle the event. The shorter the dispatch latency, the faster the system can respond to events. This is important for real-time applications. Once the right process has been chosen, it starts running to handle the event. In real-time systems, it is especially important that the amount of time it takes for this process to run is predictable and within certain limits. This is so that the system can be reliable. The response interval is the total amount of time it takes from when the event happens until the real-time process finishes running. This is a very important metric, especially for real-time systems. If the response interval is too long, the system may not be able to work properly for some real-time applications. We are learning about the dispatcher by looking at examples of concurrent execution of processes. Concurrent execution is a way of running multiple processes at the same time, which is essential for multitasking systems. In this example, the main memory is divided into different sections, each of which is assigned to a different part of the system or to a different process. The dispatcher is a very important part of the system that manages the execution of processes. It makes sure that each process gets a chance to run. Processes A, B, and C are three different processes that have been loaded into memory. Each process has its own section of memory. The numbers such as 5,000, 8,000, 12,000 represent memory addresses. The program counter, also known as the instruction pointer, keeps track of the address of the next instruction that the CPU needs to execute. In our example, the program counter is pointing to address 8,000. This means that the next instruction to be executed is in the memory section that is assigned to process B. Even though only one process can be running at a time on a single core system, the rapid switching between processes makes it look like multiple processes are running at the same time. The diagram of this example shows the system at one point in time during this stance of execution. Using the snapshot from the previous slide, we will continue to use the same example to show the traces of processes in memory space. The dispatcher is located at memory addresses 100 to 105. Figure 3, 2A shows the traces of process I will go through while it is running. The memory addresses for process are 5000 to 5011. Figure 3, 2B shows the traces of process B will execute. The memory addresses for this trace are 8000 to 8003. Figure 3, 2C shows the traces of process C will go through during its life cycle. The memory addresses for this trace are 12,000 to 12,011. Now that we have learned about individual process traces, let's look at how all of the processes work together. This diagram shows how processes can run at the same time in an operating system. In this example, CPU cycle time for each process is 6. At the same time, the execution sequence is the processes run one after the other and none of them are given priority over the others. The shaded areas in all tables show how much time the dispatcher takes to run. Columns 1 and 3 are the number of instruction cycles. Columns 2 and 4 are the memory addresses where the instructions are executed. Based on the setup, let's take a look combination of all traces of processes in figure 3.3. Processor starts running at memory address 5000 and goes to 5005. Then it gets a timeout and gives up the CPU after 6 cycles. Next, the dispatcher takes over the CPU usage within 6 cycles as shown as the first shaded area at 100 to 105 of memory addresses. The dispatcher is running to figure out the next process to deliver. Now process B starts running after process A gets its first timeout. It executes instructions from 8000 to 8003. After 5 cycles, process B needs to do something that takes time, like read from a file or write to a file, so it stops running for a while. Again, the dispatcher process takes over the CPU resource for another 6 cycles to figure out the next process to run. The dispatcher using the same memory spaces as before, within 100 to 105 as shown in second shaded area. Next process is process C because the execution is based on sequence without any priority. Process C starts running after process B needs to do something that takes time. It executes instructions from 12,000 to 12,005. After 6 cycles, it gets a timeout. The dispatcher is taking over CPU resource again to figure out the next process to be executed by CPU. Later, processor starts running again at 5006 and goes to 5011. Then, it gets another timeout after 6 cycles. Dispatcher taking over again the CPU resource to figure out which process needs to run with CPU. As usual, dispatcher took 6 cycles CPU times to execute. In memory, only process C left. So, process C is executed until timeout, which is 6 cycles. On the next slide, we will use a Gantt chart to visualize this example for better understanding. In the previous slides, we looked at traces of processes to understand how the dispatcher works. In this slide, we will use a Gantt chart to show the same concurrent execution process. We use Gantt chart to show how multiple processes run at the same time and their states over time. This diagram is very important for understanding how process states change in a real operating system. Processes do not usually run by themselves. Instead, they change state many times, which determines how they interact with the CPU and other system resources. Let's talk about the Gantt chart on this slide. The process states are distinguished by color and pattern. Black represents the process that is currently running on the CPU. Gray represents the process that is ready to run but is waiting for the CPU to become available. The check pattern represents the process that is waiting for something to happen, such as an eye or operation to finish. We will not discuss the details of concurrent execution of processes, as we already did that in the previous slide. Instead, we will focus on how this Gantt chart represents concurrent execution. As you can see, the Gantt chart starts with process A. For the first 6 CPU cycles, process is running, which is shown by the black block. At the same time, processes B and C are ready to run, but they are waiting for the CPU. After the first 6 cycles, the dispatcher takes over the CPU for the next 6 cycles. The dispatcher gives the CPU resource to process B in the next cycle, and process B becomes the running process. However, process B stopped running at cycle 5 because it requested an eye or resource. This process repeats until all of the processes are finished or terminated. The dispatcher runs from time to time, mainly to move processes between states. When it is active, it is either giving CPU time to a process or changing the state of a process.